This session is Mr. Mainak Sen, and I'd request Mr. Sanjay Chatterjee, Chair of Analytics SIG NASCOM East and CEO of IIT Analytics, to be please there on the standby to felicitate Mr. Sen after he finishes with his speech. And after that, Mr. Umang Oberoi will make his presentation. And for that, I'd request Mr. Gautam Banerjee, President DSF, to be around to do the felicitation. So let me now call upon Mr. Mainak Sen, Director Business Brio. He'll be making his presentation. The topic is collaborative filtering.
Am I audible now? Okay. So I wanted to talk about recommendation systems. Actually, a very particular algorithm on recommendation system. It's called restricted Boltzmann machines. Nowadays people fancy a little complicated stuff. So this is a type of a neural net, a very particular kind of a neural net that has proved to be very useful for these kind of systems. And I will share one of the perhaps most famous examples of this case. So let us just look into what a recommendation system is. I believe most of you are aware of what is generally meant by a recommendation system. It's like when you shop online for from Amazon or Flipkart, or so they give you product recommendations. So this is one snapshot. So items that they recommend, the site recommends to you based on your past history. And the similar kind of things happens for example, if you are watching a YouTube video. So you will see something like up next, where that up next, whatever is up next, that is actually determined algorithmically by there's some background algorithm that's running based on your clicking habits, on what you are clicking, what you have watched in the past, what similar people have watched, they give you a recommendation. So that's another application. And the same thing with news. So if you subscribe to an online feed, or if you follow a online newspaper, they give you suggestions. This is from the Washington Post, so it's suggesting what articles you might be interested in. Now there are very broadly speaking, two main classes of recommendation systems. I mean, how they are designed. So one is a content-based system. So when we say a content-based system, what is meant is that depending on the content of the product, it gives you a recommendation. So if you like horror movies, if you have watched 5 horror movies, then it will recommend another 3 horror movies to you. So that's content-based. And the one that we are going to look into now is something called collaborative filtering. So instead of, in contrast to content-based system, what a collaborative filtering system does is that it actually looks into the products or items that other users have used and kind of try to group these users, and based on that commonality that it can find from the different users, it gives a suggestion. So that's the idea. Now, to make it a little concrete, so the background model that on which the content collaborative filter is based is called a utility matrix model. So what is an utility matrix? It's a very simple array. Where you have this, so for example, these are movies. So you have 6 movies. I'm just giving you a small picture of this, and you have like 6 users, and on a scale of 1 to 5, these are the ratings that these users have given to the movies. So you see that red question mark there. So the task is, what will user 4, how will user 4 rate movie number 3? So if you can predict that, what essentially it's telling you, that if user 4 is browsing, then you might, if that score is high, if that predicted score is high, then you might as well show that as a recommendation. that, okay, you might be interested in watching this. So that's the basic goal. You want to predict the score. Now, two very important features of this utility matrix is, and this is the key idea that makes it very difficult, is that these matrices are extremely sparse. So what we mean by sparse is that you might have like a database of 20,000 movies or maybe 100,000 movies, and you have maybe 500,000 users. We're going to see a case. And but if you look into the subset of users, a particular user probably have watched only a few hundred. So most of the values in those rows will be missing, right? So that's the sparsity. So you have to basically predict the blanks. That's the task. And it's and what makes recommendation system unique to the digital world is that, you know, when we had brick and mortar stores, there was no question of a recommendation system. Why? Because there were physical constraints that prohibited you from storing everything, right? So if you run a, you know, corner grocery store, you are limited by the shelf space, right? What you can show and what you cannot, what you can stock and what you cannot stock. But once you go online, that limitation is not there, right? So you have to basically stock everything, and that's why recommendation is required. Now coming to one kind of a particular algorithm that is used for doing this, and doing this pretty well. So it's called a restricted Boltzmann machine. It's a fancy name. Believe me, the origins are pretty old. So this guy, Ludwig Boltzmann, a physicist, he died in 1906. So the idea originated from him, not of course as a recommendation system. He wouldn't even understand what a recommendation system is, but he was a he was a physicist, and he was one of the pioneers of statistical mechanics, and basically he discovered something called the Boltzmann distribution, which you see there. Those of you who are scared of maths, don't close your eyes, don't look at that, but that's what he came up with. And that's being used in this guy, by this guy. Now this guy, I don't know how many of you have heard of him. He is he's known as the godfather of deep learning. So his name is Geoffrey Hinton. He currently, I think he works with Google. He was a professor at University of Toronto. He's around 70 years old, and he came up with this idea of the Boltzmann machine way back, I think, in the early 80s. I have the paper cited here at the end. I think it was early 80s. So it's a pretty old idea, but like many of these older ideas, it laid dormant for a few decades. Nobody really used it. One major reason was that it was computationally not tractable. Computationally, it was very intensive. People were not able to actually use it because of the lack of computing power, and as well as the algorithm itself was difficult in the sense that it didn't converge. Now, in around 1998, he came up with a modification, a particular algorithm that I will just briefly touch upon, to solving the restricted Boltzmann machine, which kind of opened the floodgates, and nowadays it's being used pretty much many places for recommendation systems, and I will share probably the most famous example of its use. Now, what exactly is, what is a Boltzmann machine from a machine learning perspective? So it's a particular type of a neural net which is used for unsupervised learning. So this is a unsupervised learner, and you can think of it crudely as a discretized version of factor analysis. Those of you who know a little bit of factor analysis and PCA, it's kind of a discretization, or you are doing factor analysis on multinomial data. Basically, that's what this is about. And as a neural net, so it's why is it called a restrictive Boltzmann machine? Because it's a restrictive net in the sense that, you know, you see the nodes, you have the hidden nodes and you have the output nodes. The hidden nodes are of course connected to the output nodes, they are fully connected, but there are no connections between the nodes in the same layer. That's why it's restricted, and that makes the maths much simpler, that makes the algorithm converge a lot faster. So that's the trick, that's the restriction actually helps in implementing this system. So how do you implement this? By the way, I should come clear. I mean, most of these diagrams I'm a very poor artist, so I cannot draw these nice pictures. So I got it from I think some website, and I'm being faithful to the user. I have given him due credit at the end. So this is not my drawing. I'm too bad for this. So so the algorithm. So okay. So let me just spend a second on this. So suppose you are doing a movie rating, and you have a user. So let's say it's you, and you have these 6 movies that you have rated, right? So that data is available to you. A particular user has watched these 6 movies, and either he has watched or not watched. So if he or she has not watched, then those will be blank. If they have watched, they have a score for this. So you have that data. That's why it's called the visible units. That's visible to you. You know that. And then there are these hidden units which are latent, which are called latent variables, and so which you don't know. There is no data about latent units. You are trying to infer the latent units from the model. So the model will tell you something about the latent units, which you are going to use later on to predict or forecast for users whom you have not seen yet, right? So and the bias is just a mathematical oddity. You can forget about that. That just helps in, you know, convergence. So forget about the bias. So there is a okay. I'll try to wrap up. So there is this algorithm that they use is called contrastive divergence. It's called CD, and basically it's a variation of something very famous which is called gradient descent. So it's a stochastic gradient descent. It's a variation of the stochastic gradient descent called approximate gradient descent, called CD. Sorry, it's an approximation. Now I'll just skip the math. It's a learning rule. We don't have time for that. I just wanted to give you an example, the most famous example. How many of you have heard about the Netflix challenge? Few of you have probably. So this, believe me, was in 2006, from 2006 to 2009 or 2007 to 2009. So Netflix, they had a recommendation engine. It was called, I think, Cinematch or something like that. And they opened this up as a challenge that if you can come up with a recommendation engine which improves upon their recommendation engine by 10%, if you can do a 10% improvement on their recommendation engine, you win $1 million, right? So it was a $1 million prize, and it ran for 3 years. So it was 18,000 movies, 500,000 users, 100 million ratings. That was the data, right? And it ran from 2007 to 2009. And so this was the prize. As you can see, it is long completed. It's more than a decade now. And the winning team, I've just highlighted that. It's called Belcourt's Pragmatic Chaos. This is the gentleman, I have the paper cited. They actually won the $1 million prize, and they improved it by 10.06%, and they won $1 million. And the algorithm they used was this one, RBM. It's a slight variation of the RBM, but that's the one that they used. So I just wanted to cite that this is not, you know, it's a little complicated, but if you can manage this, you might win someday $1 million. So with that, I will end, and thank you. And there's a bibliography. If some of you want to catch up, you can send me an email, and I can share the sources with you. Okay, thank you.
Any questions, please?
The first matrix, what you have said,
Huh.
the distribution, exponential distribution, that Boltzmann distribution, what you are saying. So, is the task is to predict. Sorry. So.
I can hear you. Don't worry.
So, correct me if I am wrong. The task of this algorithm is to find out which are the states will have the high probability in that.
The task of the algorithm is very simple. The task of the algorithm is that if you have an user, correct, and you have, maybe he or she has watched, let's say 2 or say 30 movies, right, and in your database you have a repository of 3000 movies, right, what 4 or 5 movies should you recommend to him or her? That's the task.
Now it is picking up that state, right? That
Correct.
one state which has not yet happened.
That's the missing value.
Missing state.
Correct.
And that state is picked up by the probability distribution, which is given by Boltzmann equation.
No, we'll take it offline.
Oh, sorry. Yeah.
Any other questions?
Hello? Doesn't work. Hello?
Yes.
I have a question. So one of the problems we typically see for recommended systems is the so-called cold start problem, where your matrix is extremely sparse. So in such cases,
all these that's what I mentioned, that all these matrices are extremely sparse. That's why I said that, though it was discovered, though the idea of the restricted Boltzmann machine came up like in the mid 80s, right, it actually lay dormant for almost close to 2 decades because people were not able to solve that technical problem, that how can you overcome extremely sparse data.
yeah, so let's say in cases where for relatively newer businesses where the sparsity is to the extent of, let's say, 95% or even higher. More than that.
Yes.
So in that case, do you think the input features, which will have lots of missing or zeros, will that adversely impact the RBM network?
No, that's what I showed you, right? That if you actually calculate the sparsity of the Netflix data that I told you, it's way beyond 99%. It's like 100 million ratings you had, right? And it was 18,000 movies into 500,000, right?
So it doesn't impact the algorithm to such extent.
You still got that result using this.
Thanks.
That's all for now. For the rest of the questions, you can take them out. May I call upon Mr. Atul Agarwal, Chair, NASCOM ERC, and Director App Software to please come up here.
Hello.